Ladies and gentlemen, thank you for turning up to this webinar, which is going to be all about what a fault tree is. And just a quick show of hands, emoji hands. Who's ever heard of a fault tree before? Just to see. So we got a couple. You can see about 6 was a peak number, so about a third. Okay, no worries. Okay, so hands down. Who hasn't heard of a fault tree before? Put your emoji hand. So those people have their hands up for if you have heard of it. Please remove your hands now and just leave your hands up for other people who have not. Okay, so I think, and obviously we have a couple of people whose hands have been cut off, at least in the emoji world or the emoticon world. So regardless of your knowledge of what a fault tree is or isn't, today you're going to get something out of this webinar. And the reason why you're going to get something out of this webinar is because fault trees help you make better decisions. And that's essentially what this is all about, making better decisions. And when I first learned about fault trees, I was taught the way most people are taught. And that is, I was taught the way that suited my teacher. So if I had a professor telling me about fault trees, he or she had usually only used fault trees in one perspective or one context. And that was a context they taught me all about fault trees. And that's not good. And because the problem with that is when you're a student and you first come across fault trees, then you tend to only ever think of fault trees as the thing that you were taught or the context you were taught in the very first time you heard about it. And that's not good. So what we're going to talk about today is how fault trees can help you make all sorts of different types of decisions. And depending on the decision you want to make, you might use fault trees in different ways or to tackle problems using different strategies. And with any luck, at least some of you who had previous experience in fault trees might understand that fault trees can actually help you make decisions that you previously didn't think fault trees could help you make. So let's dive into what a fault tree is. Let's start by looking at a tree. And this is a tree. It's a pretty sickly looking tree, but hopefully this satisfies most preconceived ideas of what a tree is. And that is a tree which has a shape focused on a trunk at the bottom with lots of branches branching out, which is where the term branching comes from, as we move up. So we have a really complicated tangled shape at the top, but a really simple trunk, single trunk at the bottom. But that's not really helpful for understanding how fault trees work, because fault trees are actually almost the opposite of that. We have a single shape at the top as opposed to the bottom. We call that the top event. And that can be some undesirable event that we are trying to understand better. And it should always be in order to ensure that undesirable event doesn't happen again. And so perhaps fault trees should be better called, more appropriately referred to as fault root systems. I'm guessing that name's not going to take off, but fault trees are actually shaped more along the lines of a root system, not the bit we see above the ground. So that's the first thing about fault trees. They're almost upside down trees. So notwithstanding, a fault tree, which you saw an example of, helps us make decisions. And those decisions can be based on what a lot of people think fault trees do, which is help us analyze system reliability. So fault trees can help us analyze systems which are made up of different components where we understand or might have some idea about component reliability characteristics. And we need to convert those characteristics into an understanding of system reliability characteristics. But fault trees can also help us conduct root cause analysis, which is a very different set of decisions. And those decisions are, what do we need to do to ensure that failure hardly happens again? And these are sort of the two most mainstream approaches people or contexts people are taught fault trees can help you out with. And usually a reliability engineer will believe that fault trees are either for analyzing system reliability or root cause analysis based on what context or what sort of decision-making process they were first taught themselves. But a fault tree is a powerful tool for all types of decisions within these two categories. But the third type of decision, or the third category of decisions, is something that not many reliability engineers or design engineers usually think of, and that is robust customer-centric design. So we're not just talking about failure here, we're talking about failure to impress the customer. And we're going to go through all these perspectives in today's discussion. So when we talk about robust customer-centric design, that goes above and beyond just making our first design a reliable design. It's making our first design an amazing and reliable design. And so that is something that is not necessarily the remit of reliability engineers. We usually believe we are here to make things reliable, but we can also use reliability engineering tools to make things amazing and reliable. And so that's what I want you guys to be aware of today. We're having three main different perspectives when it comes to fault tree analysis. And these are the ones we're going to focus on the most. And before you even think about working out what perspective you're going to drill down on, it needs to come back to the decision. What decision are you trying to make? Because once you understand the decision, then you can work out what tools you can use. One of those tools is a fault tree. So the first perspective is using fault trees to model system reliability. And so very first thing we're going to do is a little bit of revision on what reliability is. For some of you, it might be actually learning what reliability is for the first time. And for those of you who've been to my webinars in the past, it can't be a webinar I deliver without the random hand of failure, because failure is a random process. And I often use this hand to represent all those different factors and uncertainties, which means that for seemingly identical systems, there will be different times to failure. It's an infuriating aspect of reliability, but that infuriating aspect, I suppose, gives us all work to do / jobs that help us earn money. And the problem with all this uncertainty is that our human brains are wired to crave certainty. That is, if for the same inputs, we get the same outputs. But in the real random world, where we have random failure processes, seemingly identical systems can have different times to failure. But just because something is random doesn't mean it's not predictable. So you can see straight away that we tend to have failures occurring here more than anywhere else. And that's something that's actually quite useful to identify. I mean, we still have a random process at heart, but there is still a pattern emerging. And so we can start using this pattern to help our understanding of that random process. But that said, this is still not a really useful visualization of the data we have. And these data points might be 100 times to failure from field data or field records, or perhaps you're able to somehow test 100 prototypes, although that rarely happens when you're doing reliability testing. But let's just say we have 100 times to failure. If we plot them on the line like this, you can see that there is a density around the line at a certain area, which is a useful characteristic to identify. But a much better way of visualizing density is through perhaps things like a histogram. This histogram has bars, and each bar represents the density, or essentially the number of dots, data points that exist at the base of each bar. So this is a much better way of us seeing where our data points tend to lie. But you can still see it's not really perfect. The histogram goes up and down. It looks like witch's teeth. And of course, the random process is going to be based on a process which looks a lot smoother than this. We don't have, for example, a period of very high frequency in the middle, followed by a period of lower frequency and then a higher frequency. That's just not how random processes work. So this histogram gives us an insight, but it's still not the best way of visualizing our random process. It's better than visualizing it in terms of just dots on a line. But there are other ways we can do this too. Now, the histogram is really good in that it aligns with our human brain in terms of how we try to characterize and summarize uncertainty. But this chart here does a really good job of smoothing out all those little peaks and troughs. And you can hopefully agree with me when I say that these data points are now creating a much smoother line, you would suggest. Problem with this line is that this line doesn't naturally align with how human brains are wired to characterize uncertainty. We much prefer characterizing uncertainty or visualizing uncertainty using those density plots, those histograms that help us understand the typical values of a random process and the extent to which those values vary to each side of that typical value. Notwithstanding, these sorts of charts here, which don't align with our human brain, how our human brain is wired, are much better at smoothing out the inherent intricacies of density charts that our data sets give us. And this becomes much more useful. And if we were to have a million, billion, trillion, quintillion data points, we would be able to essentially reduce all those data points to a beautifully smooth single line. And this line is reliability, the reliability curve, which you can see changes over time. Now, just to be clear, reliability is something that we often aspire to understand, but we can never fully understand because as a rule, we only ever get to see reliability or glimpse reliability through how we interpret random data. That is, how we interpret those times to failure in a test or how we interpret the field data. And so every system or every component will have a reliability curve, even if we can't see it. Now, as a rule, we're only interested, as a rule, we are able to use our reliability curve to help us work out what the reliability of our system is at different points in time. But as a rule, we're only interested in the really early part of our reliability curve. Most system requirements allow for failure probabilities of 10% or less. As if you are having more than 10%, more than 15%, more than 20% of your systems fail, it's time for something drastic to happen. And that could be servicing, where this is the reliability curve of a gasket. And you would conduct servicing before this gasket or a significant number of gaskets failed. Or if it's a military vehicle, if these things are failing, and I mean systemically failing, so you cannot get them back into service, once 10% of your fleet have failed, it's time to move on from that particular vehicle and perhaps upgrade your fleet. So as a rule, most reliability analyses focus on the early part of this reliability curve. So for example, we can use this reliability curve to work out when the reliability of our system will drop to 95%, which is a typical value for warranty reliability. So this allows us to work out what our ideal warranty period might be. If our business plan allows up to 5% of our things to fail and us to initiate warranty action on those 5%, our reliability curve, if we can find it, can help us identify what the warranty period for that system should be. And we do this by creating a system reliability model. Our system reliability model, we're going to represent with this 3.5-inch floppy disk. And I put this in here mainly because I realized how old I am getting. And when I was a young kid, I was obviously tortured by adults when they always reference things that were around when they were kids but don't exist anymore. So right back at you to all you youngins out there. This is a 3.5-inch floppy disk, which back in the day was state of the art. But in this case, this 3.5-inch floppy disk represents or contains information. On this disk, we have information that's stored in the form of a system reliability model. And that model helps us relate component reliability characteristics to system reliability characteristics, which is something that might be absolutely essential if we're trying to understand what the warranty period should be for an entire system and not just a component. And the idea is once we have this system reliability model, we can insert it into a data analysis machine. And this data analysis machine starts with data. And in this case, it's going to be component reliability characteristics, combines that data with a system reliability model, and out the other end spits out information in the form of system reliability characteristics. So bringing it back to the decision, we would only ever do this if the decision maker for an important decision needs to know certain reliability characteristics, like what the optimal warranty period should be, for example. System reliability model is very good at helping out those sorts of decisions. And so here's an example fault tree. That fault tree starts with a top event, as I've already mentioned. And that top event for our system reliability model or system reliability analysis is usually going to be some sort of system level fault or failure. Excuse me. And so we're going to now use a fault tree which starts the top event to help us create the system reliability model that's going to go on our 3.5-inch floppy disk. Now, beneath the top event, we usually have two different types of events or shapes in a fault tree. And so all you need to do to understand how a fault tree is put together is understand these basic shapes. You start with the top event, which is that it's not a rectangle, it's not an oval, it's not an ellipse. It is a shape which, I suppose, a rectangle with corners on it. Not sure what the correct term for that shape is, but it's not a circle or an ellipse. We reserve that shape for another part of the fault tree. And that shape is that part of the fault tree, parts of the fault trees that we call basic events, which in many cases are component failures or environmental events that we call faults. And that's where the name fault tree is derived from. Initially, when they're coming up with fault trees, they use these circles or basic events to represent what they called faults, something going wrong. And fault can be a broad term when you use it in certain contexts, or it can be a very specific term when you're doing, for example, root cause analysis. But notwithstanding, in this context, fault is a very broad term. And so this is one of the shapes that you'll see in a fault tree. The other sorts of shapes are called logic gates, when they represent an event that contains certain combinations of other events. So, for example, you have these two shapes are the most popular or dominant shapes you'll see in a fault tree. The one on the left with the rounded top and the flat bottom is called an AND gate. And that means all of the events or gates below that shape need to happen for that event to happen. This one over here at the round top and the round bottom is an OR gate, where any of the events or gates below need to happen for that event to happen. Now, this is getting too wordy. Obviously, a lot of words up here and only a few shapes. So we need to really reinforce these definitions through examples, and that's exactly what we're going to do. So let's look at a system which has two pumps and in parallel. And this system will fail if pump A fails and pump B fails. We call this a parallel system because in many physical layouts where a system can work, if only one of these components is working, they actually arranged in the plant or in the vehicle in a configuration that looks parallel. You can see the pump on the top is on a pipeline, which is parallel to the pipeline for the pump on the bottom. Pump A's pipeline is parallel to pump B. So we call this a parallel system. It simply means that we only need one of these components to work for our system to work. So one of these pumps is a redundant pump. And we can use fault trees to help us understand this particular system. So what we're going to do is we're going to define two basic events. Each basic event here corresponds to a pump failing. So the top basic event, which is now represented with a circle, is the event where pump A fails, and the circle on the bottom corresponds with or represents the event where pump B fails. And we're going to make this a little bit simpler. We don't want to keep drawing pumps. That's going to take us a long time. And as a rule, reliability engineers are not renowned for their realistic sketching skills. And so what we do is we replace these pumps with component identifiers, which can be words or just letters, which help us understand what those basic events refer to. And so in this case, we're going to replace the pictures of each pump with the letters A and B, because we know that A refers to pump A and B refers to pump B. This makes things a lot simpler. Now, remember, the system works if one of these pumps works. So this is what the fault tree looks like for our system. There is a top event, which in this case is system failure. We have this gate here, which is an AND gate, which means that all of the events or gates below need to happen. So the top event is a system failure, and the AND gate requires all events or gates below for it to happen. So let's just say pump A fails, which means that basic event A has occurred. Now this red line represents a fault propagating up towards our top event of our fault tree. Our pump A failed, and then it turned red to represent that failure event occurring, and that red line represents a fault propagating or trying to desperately get to the top of our fault tree. Unfortunately, because it hits an AND gate, and it's the only event that feeds into the AND gate that occurred, the AND gate says, no, you can't pass here. So the system, this shows how we can represent on paper a system that requires both pump A and pump B to fail before the AND gate allows the fault to propagate towards the top and cause system failure. So when we're using fault trees to model parallel system reliability, we often see an AND gate, because an AND gate requires all of the events or gates below to happen, i.e. all of the components to fail before it allows the fault to propagate towards the top. So this is how we can represent how a system behaves when it comes to reliability if it's a simple parallel system. But of course, there's a lot more systems like than parallel systems out there, such as a series system. Now, in this system, we need both pumps to work. We have the first pump pumping fluid up to some level, and the second pump then pumps that fluid up, which is now at a higher level, to wherever it needs to go thereafter. So the system fails if pump A fails or pump B fails. Now the key word here is or, and the keyword or applies to series systems. So the keyword and applies to parallel systems, and the keyword or applies to series systems, because we need pump A to fail or pump B to fail for our system to fail. And now corresponding fault trees still based on the same basic events. Remember, basic events are represented by circles, sometimes ovals or ellipses, in which we don't want to draw a pump each and every single time. So we replace our pumps with A and B, or what we call component identifiers. And we are able to create an entirely different fault tree based on an OR gate, because we still have the top event, but now the logic gate has a rounded bottom. And so it means that any of the events or gates below need to happen for a fault to propagate all the way to the top. So let's just say that pump B fails, and now we have a fault trying desperately to get to the top event, which is able to easily do because the OR gate will occur if any of its input events occur. And so these two fault trees model basic system, parallel and series systems. But of course, not all systems are basic and parallel. So for example, here's a slightly more complex system where we have a holding tank on the left-hand side, which is connected to two pumps, pump A and pump B, which are in parallel, and then a single valve. And so we can see here this pump is neither exclusively series nor exclusively parallel. How do we use a fault tree to model this system? Well, we can see from a high level that we have three events, not all basic events, but just bear with me. We can see that we have what looks like a series system if we look at the pumps, the parallel pumps, as a single event. So if the holding tank fails and all the pumps fail, or the valve fails, we have system failure. So these three events actually are configured in a serial way, so that if any of these the holding tank fails, or the pumps fail, or the valve fails, we have an OR gate, which represents the fact that a fault can propagate to the top event if any of those things occur. But we can see that we can have a basic event on the left-hand side, which represents holding tank failure. We have a basic event on the right-hand side, which represents valve failure, but clearly the stuff in the middle, which isn't a basic event yet. And that's because there's more than one component, but we know how these components are arranged. So we just represent that area we circled, those two pumps, with the AND gate we derived from the analysis of our two parallel pump system. We can replace all these images with component identifiers, and now we have a fault tree which represents our ever so slightly more complex system. And if you understand that, well done, you know how to model all sorts of really complicated fault trees, because modeling systems with fault trees is not complex or complicated, it's just tedious. That's all it is. You just need to work your way systematically from the top all the way down the bottom. And here's an example of an even more complicated fault tree, which is it's not even that complicated once we break it down into little bits. So this is a secondary cooling loop of a nuclear power plant, and all nuclear power plants have a reactor core, which is obviously a bad place in terms of toxic exhaust and radiation and everything else. So reactor cores are located within a containment vessel. And the idea is that these containment vessels are able to hold leaks of any of the bad stuff, which in this case is going to be most likely be the water, which is in direct contact with the nuclear fuel, the uranium that is reacting to create the heat. And so this water, which is inside and touching the fuel, we never want it to leave the actual containment structure. And so we have a heat exchanger which takes heat from the water which touches the fuel rods and transfers that heat to another body of water, which is in the secondary cooling loop. And then the water in the secondary cooling loop is the only water that is allowed to leave the containment structure. It turns into steam, goes to a turbine, creates electricity. The steam is then condensed back into liquid water. And then main and auxiliary valves and pumps pump that water back into the containment vessel, into the heat exchanger, and the cycle repeats. So this is a slightly more complex system. But even then, creating a fault tree for this system is relatively simple. We just need to be systematic. And so if we will look at this fault tree, how do we do that? We can see that we have what appears to be some series systems, some parallel systems, some more series system. How do we go about doing this? Well, first thing you want to do, as a rule, this is how I like doing things, is to you can either look at it from the top or looking at it from the bottom. And you might want to look at the main auxiliary valve pumps and say, geez, that's a bit of a mess. You can see that's quite a complex little part of our system. And so what we can do is just put a circle around that and say, we're going to deal with that one later, because everything else looks like it's arranged in series. That is, if the heat exchanger, the turbine, or the condenser fails, or the main auxiliary valve pump subsystem fails, we have failure. Now, in this context, I'm just going to use some diagrams of some of our basic events to help us understand what these basic events refer to. The reason I'm doing this is because we're not all nuclear engineers, and in this case, it can be useful to at least for this exercise, keep some pictures there to help you remember what these basic events refer to. And so now we have a basic series system. Now, for some reason, my computer here is putting a little vertical line on the edge of my top event shape. Please ignore that. It's the bane of my existence. For some reason, computers like doing that when I do these sorts of lessons. That's a visual artifact, which I'm going to attempt to remove again after we're done. But you can see here we have a basic series system where if the heat exchanger fails, or the turbine fails, or the condenser fails, or the main auxiliary valves and pumps system as a whole, that fails, then we have secondary cooling loop failure. So now we're going to look at the bits we haven't developed into basic events yet. And we can see here that we have two valve pump pairs arranged in parallel. So we use an AND gate for each valve pump pair, but each valve pump pair will itself fail if either the valve or the pump fails. So that's a series system, series subsystem. And so we need to use an OR gate for these two valve pump pairs to complete our fault tree. Again, when my computer decides it's going to join this webinar, it's going to show you exactly what that looks like. And you can see here, we now have two OR gates, which represent those two valve pump pairs. And so again, creating a fault tree is not challenging. It's just tedious. You just need to be systematic. Usually I prefer to start working at the top. And if there's work out if there's at the highest level, if there's a series system I can see, and if there is, I draw circles around the complex bits which form part of the series system, and then move on. You can see here we have our top event. We have an AND gate, we have an OR gate, and we have all these basic events. So this is a basic system reliability model that a fault tree can help us out with. And that's fantastic. Now, the other thing is that in some textbooks or guidebooks, you'll see OR gates which have this plus sign in it. You'll also see AND gates which have this circle or dot in it. These aren't special. The only reason we see these sometimes is because it can be difficult to visually differentiate between AND and OR gates because they do have a similar shape. And so sometimes we add plus signs and sometimes we add circles or dots to help those who are harder of seeing from easily or more easily differentiating between AND and OR gates. So these aren't special variants. Those are just different ways of representing AND and OR gates. And so here we have our system reliability model with a fault tree. And you can see here that if one of our valve fails, the fault's going to desperately try and propagate its way up. It's going to hit an OR gate, go straight through, and then it's going to hit an AND gate and stop, because an AND gate requires all input events to occur. Even if the pump next to that failed valve fails, it's still not going to change the system function. But if one of the valves on the other assembly fails, then it completes the AND gate, which then goes to the next OR gate, and all of a sudden we have system failure. So all these AND gates and OR gates help us do is work out which combinations of components need to fail for our system to fail. That's essentially what a system reliability model is. And that's what makes fault trees very, very powerful. But this is one of the most common interpretations of what fault trees can do. But fault trees can do a whole lot more than this, because fault trees can help us do root cause analysis. And this requires us to take off our system reliability model hats and put on root cause analysis hats. And people might say, well, that sounds relatively similar. I'm trying to understand why things fail or what parts of what components need to fail in order for a system to fail. That sounds a little bit root cause analysis, but it's not really. And the reason why is because root cause analysis helps us understand why things fail. And the idea we want behind that is because we want to understand what we can do to then stop things failing in the future. So a system reliability analysis fault tree like this one will help us understand what needs to occur for system fault or failure to occur, where each basic event typically corresponds or represents a component failure. That's not how fault trees for root cause analysis work. When it comes to root cause analysis, we look at things very differently. It can be any undesirable event that has already happened as a rule, which can include system failure, but it can also include things like why our business isn't profitable this quarter, or it can also include why a certain component is behaving in a way we didn't expect. That might not be failure per se, but it might be something we need to better understand. And the basic events are potential root causes for any of those undesirable events. And this is very, very key to understand that these shapes are very different as a result. Now, a root cause is often defined as the initiating cause of failure, which isn't very helpful. A root cause is actually the thing we need to change to make sure that failure hardly happens again. So if you can't influence that potential root cause, then it's not actually a root cause, it's an environmental factor. So that's where the term initiating cause of failure is not particularly helpful, because an initiating cause of failure can be anything you want, depending on context or perspective, or what you'd want to be responsible for, or how quickly you want to get out of that meeting before lunch, or how much blame you want to heap on somebody else. A root cause is a thing that you can change to make sure that failure hardly happens again, which is very, very different to what most textbooks suggest a root cause is. So if we look at a smart lock, for example, and this is one of my consistent examples in these webinars, and smart lock's a wonderful combination of different technologies. Let's just say we have some sort of issue where, for whatever reason, it's not working. When the handle's not turning, when the handle turns, the bolt's not going in. And the smart lock itself comprises of, in this case, 17 different components. 16 are different because we have 2 handles. And you can see we have different types of components. But the things I want you to focus on are the PCB, the electronic componentry, and the electric motor, which is the most important part of the smart lock from one perspective at least. And the reason why our smart lock's not working is because our solder joints have fraction. So what is the root cause of this particular failure that we've come across? This is not cool. And the thing is, we need to focus on the things we can change to make sure that this failure happens again. Now, can we change the fact that this solder joint has fraction? We can't change that. So if we can't change it, because that's actually a symptom, it's a physical phenomenon that's occurred, we cannot then classify this as a root cause. This gives me no information on what I need to do differently to make sure this failure happens again. And so because this isn't a root cause, we need to dig a little bit deeper. So we dig a little bit deeper and we understand how this thing is used. And then we realize that perhaps when we slam our door, the forces being transferred to these solder joints are actually putting shock stresses on these solder joints we didn't really think about or didn't anticipate. So are door slams the root cause? Again, remember, a root cause needs to be something we can change in order to make sure that failure doesn't happen again. So can we go and ask our customers to stop slamming the door? And the answer is clearly no. So because of that, door slams are not the root cause. But perhaps in this investigation, we now start thinking about door slams in a different way, and we might need to add them to our user profile. But nonetheless, door slams are not the root cause of failure. Now, if we think about this from a different perspective, perhaps because the doors are slamming and transferring this force, are these solder joints doing something they weren't designed to do? Are they actually being required to physically restrain cables with much greater force and strength than they're actually capable of doing, even if this was coincidental or accidental? Is this the root cause of failure? That the fact that they're doing something that they weren't designed to do? Is the design being incapable of tolerating shock loads at cable connections? Is that the root cause? If that's something we can change, then we're onto something. And because in this case, we can change the design, now we're able to think about corrective actions that are able to mitigate this particular problem. This could start with thicker gauge wire to provide a better contact area with the motor terminal, shorter wires that accumulate less momentum, physical clips that secure the wires to the cable, to the housing of the smart lock. Could also include a socket and plug at the PCB end instead of solder joints in the circuit board, which has added benefit of making this thing easier to assemble. It could also include testing, where we visually inspect motor solder joints, because sometimes it's easy to pick visually when solder joints haven't taken properly. And perhaps we're going to do another corrective action, could be surveillance automated microscopic optical inspection for 10% of incoming motors, because we know that solder joints defects can be invisible to the naked eye. And if we might also conclude that if our supply isn't doing a good job of soldering, we're going to pick it up if we do 10% incoming inspection sampling. So now, because we focus on the root cause, which wasn't doors slamming, which wasn't something that we can't control, we are now able to get corrective actions. So root causes are not the initiating cause of failure. They are the things that we can change to make sure that failure happens again. And often root causes are embarrassing because they're oversights. They are things that you own that you didn't do or could have done to prevent failure from occurring. And when it comes to failure itself, I often like using an apple to represent failure events, especially when it comes to root cause analysis, because these failure events, these apples, can now be seen as fruit of this tree of failure. But a tree of failure, which represents the process that infuriatingly causes our smart lock to fail, will cause or create lots of different types of failure, lots of different types of apples of all different shapes and sizes. We might have critical or severe failures, which affect safety or incur millions of dollars of losses, or catastrophic explosions or complete shutdowns. They are bad failures, and for that reason, we might use bigger apples to represent those sorts of failures, whereas a minor failure, which could be, let's just say, an annoyance or an aesthetic change, we're going to represent that with a smaller apple. But nonetheless, all these apples grow on the tree of failure. Now, the approach to dealing with these apples can completely vary based on the perspective that you're focusing on. So you could just simply remove these apples, i.e. repair them, patch over them. The infuriating thing about the tree of failure is that it will always grow back because it's a tree, and it will start sprouting fruit again. And after we repair those failures, they're just going to happen again. And that's because when we talk about root causes, it's based on the root of our tree of failure. We need to get dirty. We need to get beneath the ground to the root cause, which results in that apple fruiting in the first place. But in practice, we like referring to things as root causes, but in the real world, there's multiple root causes. Sometimes we call them causal factors because root cause sounds somewhat singular, but either way, there's usually lots of factors which need to contribute or combine to help our tree grow. Now, these are the things we need to address in order to stop having to continually remove apples. That's what we're trying to do. And that's where root cause analysis is very different. So root causes are things you can do something about. Can you simply design, blame the supplier for and assign supplier issues as the root cause? The answer is no, because that's simply blame and avoiding responsibility, because that's something you can't control directly, at least as written. But if you look at root causes from the perspective of things that you can control, did we place too much time pressure on the supplier? Did we not establish a collaborative reliability strategy with the supplier? Were there incorrect specifications provided to the supplier? Was design not robust? Do we have a poor manufacturing culture with our suppliers? Is there minimal reliability manufacturing and quality training amongst our suppliers as well? These are things we can influence. For example, Boeing simply just demanded that all its suppliers essentially halve the amount of money they were charging Boeing. To say that Boeing didn't influence the root causes of failure that were now present in these aircraft components that we're now receiving is just sheer nonsense. The root cause of many of those failures is a decision Boeing made to simply demand that suppliers cut costs arbitrarily. But these are all things that we can now control. So if you're interested in improving reliability by making sure you focus on root causes that you can address, you will now start to improve reliability. And by the way, usually have much better relationships with your suppliers. Now, many root causes look like these people, which I'll explain in my attached workbook. But for people who have been to many of my webinars in the past, these are the enemies of reliability, which I talk about. I'm not going to talk about in great detail today, but we have on the left the process zealot. In the middle, we have the ponderous professor who just loves equations and studying things and not making decisions on the right. We have the infant manager who wants the wrong thing fast. And I dare say I don't need to explain these people in too great a detail for those who have never heard of them before. for you to know exactly who I'm talking about. Root causes are usually decisions made by people like this or people acting like this, or at least for a very short period of time. So once we have a root cause identified, we can come up with corrective actions. And that's what root cause analysis is all about, even though the name doesn't suggest it, because if you don't, all you're doing is admiring problems. Unless you come up with corrective action, all you're doing is admiring that problem you worked hard to get. And so the idea in reliability engineering is to solve problems by finding the vital few corrective actions. And the earlier you do this, the better it is. In fact, if you embark on finding these corrective actions and embedding them in your first design, they're usually fast, simple, and free, much like those design characteristics we came up with for our smart lock. So it's all about finding those corrective actions. So if we look at the issues associated with our soldering, solder fractures in our smart lock, if our suppliers, if we simply say suppliers poor soldering, or the customers are slamming the door too hard, or the testing was too harsh, we need to make testing easier. These aren't root causes. These aren't things we can influence. These aren't just saying this to get that meeting finished and make sure you don't have to do anything before Friday. Means that you have not addressed the problem. These are things that you cannot address, at least directly. But if you design robustness into your design, or perhaps work on establishing better harmonious or working with your suppliers in a more collegiate way, that's when you get robustness based on finding root causes, things that you can do to influence good design. Now, the third thing that I talked about at the very start was how fault trees can now help us with robust customer-centric design. So we've gone through how fault trees can help us do system reliability modeling. We've also looked at how fault trees can help us do root cause analysis in terms of working from the top and getting to the bottom. There's examples in the workbook I've attached, provided to you. But the third way we can look at fault trees at helping us out is through robust customer-centric design. So what does that mean? Well, as a rule, we tend to look at failures as top events in a very engineering technical way. A failure occurs when our system has lost a function which is defined in specifications that satisfy requirements, etc., etc., etc. And when a failure occurs that loses a function that breaks us a specification, so we no longer satisfy a requirement, that is what we call a failure. Very textbook, very clinical, sometimes very narrowing. So let's look at Blackberries, for example. And some of you might remember Blackberries. They're a little bit more contemporary than 3.5-inch floppy disks. But Blackberries, they were very reliable. But what set Blackberries apart was their physical keyboard that allowed users to more easily answer emails, which in the early 2010s was kind of a big deal, especially before the functionality that we now associate with smartphones was starting to emerge. And so people really valued their ability to really rapidly respond to emails, and that meant physical keyboards were very popular, which is why Blackberries were very popular. In fact, Blackberries bet their house on manufacturing products which always had physical keyboards. But that was a problem because they were not customer-centric. For a time, their vicious focus on having physical keyboards aligned with what customers wanted. But when customers changed, BlackBerry failed to change. And so if we look at failures from the perspective of no longer making our customers happy, then we can use fault trees in a very useful way to help us identify what we can do to actually make our thing better than our competitors. So if we go back to our smart lock, and instead of looking at the smart lock in terms of physical failure, let's look at the smart lock itself as the object of our analysis from the perspective of our customer. So let's just say a user or customer who's going to buy a smart lock, they want the smart lock to do something. Usually, they want to be able to get through the door. That's what a smart lock is there to help us do, allow us to get through doors. And if our customer can't get through the door that our smart lock is attached to, that is a bad thing. This is why it's always important to look at things in terms of requirements. We can often get enamored with Bluetooth this and unlocking speed that, and just forget that at the end of the day, we are here to help our customer get through the door. So one of the reasons our customer might not be able to get through the door is because they can't remotely open the smart lock, which is what our smart lock is there to do primarily. For example, our smart lock can automatically detect when our smartphone is in our pocket as we approach the smart lock and automatically unlock. So if our smart lock can't do that anymore, our customer can't get through the door. This might happen from time to time. And if that happens, if they can't remotely open the smart lock, then the customer can't get through the door if they then can't also get open that smart lock using a manual approach. So for whatever reason, they forgot their phone or the phone switched off, they now need to get through the door manually. So if they can't do that either, then our customer can't get through the door. And perhaps when we're doing root cause analysis, or fault tree analysis for robust customer-centric design, as we're brainstorming our way down, we might think of or try and categorize different ways our customer can't get through the door. But if we are not convinced that we've exhausted all avenues of brainstorming, then we can add this event on the right-hand side we call an undeveloped event, which we just in this case label other. And all that means is that at the moment we are reasonably comfortable that the two ways our customer can't get through the door are the main ways, but we might want to come back later on to think of different ways our customer can't get through the door. When we're doing fault tree analysis, always resist the urge to get too detailed too quickly. Because when you get too detailed too quickly, that's when you rush to your favorite root cause or your favorite basic event, as opposed to all possible basic events. And so what this means now is that we have the start of a fault tree. These are what we call functional failure modes, where we describe what our product can't do that it's supposed to be able to do in order to make our customer happy. And so because they can't get through the front door, we might now investigate, or in this hypothetical scenario, we might investigate what might lead up to these two different functional failure modes. So if we focus first on our customer can't remotely open the smart lock as they approach it, we might categorize this into different ways that this can't happen. Maybe our customer can't communicate with the smart lock via phone. Perhaps our customer can't our smart lock can't inherently transition to an unlock state. Now, what that means is that in one scenario, a customer can't communicate, can't physically or electronically tell the smart lock to unlock. In the second scenario, perhaps our customer can tell a smart lock to unlock. The smart lock cannot inherently do this, might be broken. And so now we have different categories of failure or reasons why our customer can't get through the door to investigate later on. When it comes to the customer can't manually, not being able to manually open the smart lock, that might be because there's a mechanical failure. And we've already done a fault tree for mechanical failure. So we're going to use this blue shape here to reference that very system reliability analysis type fault tree we've done earlier. Perhaps we've done another one for vandalism or crime. There's another fault tree for trying to our smart lock failing due to robbers and burglars and home invaders trying to assail or damage our smart lock. And there's all sorts of different types of things that we can think of, that we might be able to think of, that can cause our customer not being able to manually open the smart lock. So if we think about this right now, what else can we put where the question mark is? This is where a group brainstorm becomes very useful, because this question mark might, when we think about it, if we force ourselves to stop, could it be caused by an installation error or a cyber attack, or elderly or physically weak customers, or incorrect door geometry, or any things that we don't automatically think of when we think of traditional reliability engineering, where we tend to focus on our doors or smart locks breaking those solder joints failing. And when it comes to installation errors, this is a fantastic thing to identify in this fault tree analysis, because if we are concerned about installation errors and understanding that our smart locks are going to be installed by a bunch of different homeowners and people who aren't trained, the corrective action could then be to come up with an installation friendly design where the installer only needs a single tool. Perhaps we create an installation video. What other things can we do to minimize installation errors? Because at the end of the day, an unhappy customer doesn't care why they're unhappy. They're unhappy because they're unhappy. So it's up to us to try and prevent them from being unhappy, because if they are unhappy, they're going to focus their lack of happiness on our product and our organization. And this is where we start thinking about robust customer-centric design. Cyber attacks, we often forget about cyber attacks. So perhaps we need to, from the very start, think about autonomous patch strategies and encryption and all sorts of other things that allow us to design a smart lock which is harder to break into. But again, these aren't traditional failures per se. And some of us might be saying, oh, but of course, if that's in the requirements or in the specifications, then if our smart lock can't do these things, then it's obviously failed. So this now becomes a traditional failure-centric fault tree. Problem is, it is almost impossible to completely understand the requirements at the start of a design process. And coming up with a fault tree like this helps us expand our understanding of what those requirements are and deliver corrective actions, which essentially focus on what our customer wants to feel. And that customer wants to feel not frustrated because he or she can't get through the door. Perhaps we need to think about an elderly or physically weak customer. Perhaps this means we need to have an automatically lit keypad. Perhaps that might mean that we have a motion sensor built in, because we now need to work out when that keypad needs to get lit up. Maybe we need to conduct a study to understand what activation forces and travels are needed for that keypad for our elderly or physically weak customer. That also might mean that we are now opening ourselves up to a completely new market segment where ours is the only smart lock which provides support to the limited accessibility market segment. So this is where you do these sorts of things and opportunities just happen. Incorrect door geometry. Do we need to study the doors of the world, so to speak? And if we if we assume that we know what the whole looks like, perhaps this fault tree's helped us realize we need to do a lot more work in order to get there. And the idea is this fault tree, where we focus on our customer experience, now gives us these wonderful things to consider during the production process that if we don't consider until later on, just will not happen. If we forget about tamper-proof integrated circuits, if we forget about installation-friendly designs, well, if we think about them later, it's too late. So if we can think about these things at the start, that's when they become effectively fast, simple, and free. Now, if we look at the motion sensor in greater detail, that's one of those examples where we now have a design characteristic. Now, this is the complete fault tree that you will find in your workbooks. And this fault tree might help us realize that we need to install an external USB port to allow the smartphone to temporarily power the smart lock. Why is that? Because what happens when the batteries are flat in our smart lock? We still need our smart lock to work, and maybe the USB port allows our user's customer's smartphone to temporarily provide that power to get in the house. Low battery warnings, updated test regime to simulate attempted robberies or vandalism, research specifications to accommodate elderly customers. These are all those things that if they don't happen, are the things that you're going to lament later on. You say, if only we thought of this earlier. And if you think of these things early, they're almost trivially inexpensive and easy to implement. But it only comes when you look at fault trees from the perspective of robust customer-centric design. So one of the key messages I always have when it comes to fault trees and reliability analysis is that we are trying to make our first design a reliable design, and root cause analysis helps us do that. We only want to do this on the vital few parts that matter the most. We want to use the correct team for our fault tree analysis. And yes, you do need to do assemble a team. When it comes to some of the things we looked at today, we want to reduce costs and schedules by identifying these issues as early as possible. So when we identify these issues early, we're able to design things more quickly, because we don't need to wait until we realize our design's not up to speed before we go back and redo work we already thought we had done. In other words, the build, test, fix treadmill. Then, of course, there's safety. Safety is a very unique, well, it's not unique, I should say, but it's a specific thing you need to think about, because not only does our thing need to work, it needs to be safe. And that means it needs to defeat hazards that range from small children through to criminals, through to yetis, through to bears for our smart lock. So we need to think about those things. And that fault tree analysis is really helpful at doing that. Reducing hazards. All those different things we looked at today can reduce the hazards essentially associated with things like door slams and all those other things that would otherwise cause a fantastic smart lock to be rendered obsolete very quickly if our competitors had already thought of these wonderful things. So it's not just about making our first design a reliable design. It's all about making our first design an amazing design. And that comes because we stopped and thought about what could go wrong. And so hopefully, and that's where I'm going to call time on our discussion today. Hopefully you now have an understanding of what fault trees can do and how they help you make better decisions. And these decisions are essentially going to force us to think. And we can often forget that we need to make decisions. We can often plow through the production process and later on realize we should have decided to do something a long time ago. And so fault trees help us, just one of many tools. And I don't want to suggest that fault trees are the only tools that can do some of the stuff I talked about today. They can help us model system reliability. They can help us do root cause analysis. They can also help us put the customer at the very front and center of our thinking in order to make sure our product is just simply better than our competitors, and otherwise help us do what it is we're setting out to do much more quickly and cheaply. So those are the three perspectives. It's all in your guidebook, so hopefully you enjoy reading through that guidebook when you need to do fault tree analysis or need to fall asleep later on tonight. If there are any questions, please feel free to throw them my way right now. And I can see that Carl has already asked a couple. So while I'm answering these questions, please feel free to keep throwing them my way. Carl asks, what is the typical cost range in doing a fault tree analysis? So the typical cost range is a difficult question to answer, but I would tend to do a fault tree analysis with between 4 to 8 people if I was facilitating that fault tree analysis, and depending on the challenge that, that your fault tree analysis is trying to overcome, you might need to have that group activity last a day or maybe 2. The other thing you need to consider is getting people trained on what a fault tree is and what fault tree analysis does. And let's just say that takes, I don't know, 8 hours. So without being able to give you a really useful indicative cost, I've at least given you some idea on how much time and how many people you need to do a good fault tree analysis. Carl also asked, what are some of the other tools in addition to or complementary to a fault tree analysis? Okay, so from the start, another really fantastic system reliability modeling tool is reliability block diagrams. Fantastic at modeling reliability of systems. So that's I would say a complementary tool because it does the same thing that fault trees can do when you're creating a system reliability model. There's pros and cons for each one, and you should use the one that you prefer the most. That's the first thing. For root cause analysis, there's lots of not competing tools. There's again, they do. There are other tools out there which do the same thing. I think the closest thing to fault tree analysis for root cause analysis is a fishbone diagram, because it allows you to find or branch out and find as many possible root causes as possible. You could also argue the 5 whys approach is another way of doing root cause analysis, but the problem with that is the 5 whys never allows you to sort of has a hard stop once you've investigated a certain distance, and you might not have got down to the level where you've reached a root cause you can do something about. And the other problem with 5 whys is it doesn't branch outwards. It usually goes down to a single root cause. We know, at least the example we looked at today for our smart lock, we came up with 6 corrective actions. 5 whys focus on a single corrective action and therefore a single root cause. And so you'll just limit yourself to the number of possible corrective actions that are available to you. And that's a big deal because you want to find as many potential corrective actions as possible, which allows you to select the cheapest ones. Your 5 whys will quickly find you your favorite root cause, and that might not be the best one. And for the last perspective, what's another tool that can do robust customer-centric design? There's so many different approaches out there. You could use, for example, House of Quality, but I've never seen that worked really well. I think that often is overwhelmingly complex or complicated for many people, and we spend too much time teaching people how to construct that house as opposed to thinking about how to make customers happy. That's why I like fault trees in that context, because a fault tree is relatively simple visually. You do need a little bit of training to be sure, but the idea is that these fault trees are primarily there to structure brainstorming. Another tool is FAMIRS. FAMIRS are all about, people say they compete with fault trees. I don't believe they do. I believe they actually have very similar approaches, but FAMIRS are a lot more, let's say, structured from in terms of identifying failure modes and mechanisms and coming up with corrective actions. To be honest, use the one that works for you. Okay, I can see you asked a ton of other questions as well. Good work, Carl. Any thoughts about Swiss cheese analysis? I mean, again, Swiss cheese analysis, if it works for you mentally, fantastic. But Swiss cheese analysis, the idea is you have a bunch of slices of cheese, and Swiss cheese is famous for having holes in the cheese, and the idea is a bad thing happens when all those holes line up. I think it's more like a Swiss cheese analysis is a visualization tool to help communicate the fact that there should be many layers of protection between especially bad failures. The idea is that when those holes line up, this means that every single layer has failed in a way. So I don't necessarily think Swiss cheese analysis helps the brainstorming process. With fault tree analysis, there is no priority, at least visually, put on one root cause over another, for example, which means that if you allow your fault tree analysis team to come up with as many possible root causes as possible, then you can prioritize those root causes or prioritize corrective actions and effectively implement the ones which are the fastest, cheapest, and freest. I don't think Swiss cheese analysis allows that sort of free thinking to occur. Now, your next question, Carl. Oh, geez, you're flying thick and fast today. There's a company called Think Reliability that specializes on the 5 why analysis using Excel spreadsheets. Any thoughts? I don't want to comment too specifically on what companies do and don't do well. And I think 5 whys definitely has a place, especially when you're doing informal risk analysis, root cause analysis. 5 whys are fantastic on the go when you're in a manufacturing plant, for example, and you have 10 minutes to work out what the root cause of failure might be, for example. So 5 whys are fantastic at helping a single person, as a rule, come up with very quick, structured ideas about what might be causing something to break. So I don't want to badmouth 5 whys. It's just that they have a place, and I don't believe that place is for more, let's call it, sophisticated. Let's everyone take a breath, everyone stop and think, as the screen illustrates. I just don't think they're quite as powerful. But I really don't know too much about a particular company, so I don't want to suggest that what they do is particularly bad. And I can see that Paul writes that Think Reliability's cumulative cause map is very similar to a fault tree. And essentially what I'm rallying against per se is the simple act of finding a single answer to that question as you ask yourself 5 whys as the way you go down. And it sounds like Think Reliability is encouraging people not to have a single answer when they have those cumulative causes, which is an approach that I support. So hopefully that answers your question without bad mouthing a particular service provider. Fish bones operate from left to right, which makes it difficult for Western cultures. Any thoughts? It's actually a valid thought that we need to think about how people best visually interpret or understand a problem. So that's where I say, when it comes to any tool, fault trees, Vermeers, RBDs, fishbone diagrams, use a tool that works the best for you. And as a rule, you need to train people to use whatever tool you're going to make happen in a group activity anyway. And I understand you say sorry from right to left, which is true. You always have the head of the fish facing the right. You know what, Carl? If your team prefers to have the fish facing left, there's no reason why you can't do that either. You have the tools work for you and not the other way around. Okay. Thank you for that feedback, Carl. Any more thoughts, any more comments, any more questions? I'm more than happy to answer them. Not just the Carl show, but more than happy that Carl, I'm really happy that Carl asked all those questions. If anybody else has any other questions, please feel free to share them now. I think we are done, Fred. Well, anyway, team, the last message I want to leave with you is the last message that I've left on the screen, which is to stop and think. Thank you, Paul. So when it comes to fault trees, what decision are you trying to make? And that often, the fact you need to make a decision means you need to stop and think about making decisions in the first place. Do I need to understand system reliability? When a fault tree can help me model system reliability. Do I need to understand why that failure occurred so I can develop corrective actions which are far simple and free or cheap? Well, then root cause analysis, where the basic events are now root causes, are very helpful. And root causes are not something that you can use to apportion blame. They are by definition things that you can address. If you're not happy with your supplier, then that is an environmental consideration. If you cannot affect that supplier's behavior, just simply blaming people is not finding a root cause to come up with a corrective action. And finally, you can use fault trees to come up with robust customer-centric designs, because at the end of the day, it's your customers' emotions which drive what a failure is. If they can't get through a door, even if they are pushing those keypads within specifications, but if they're an elderly customer and they're pushing as hard as they can, and they can't seem to make that keypad work, then in their mind, your product has failed. Doesn't matter what you internally believe they should be doing, your product has failed. And fault trees are really good at helping us work out if we need to have motion sensors, USB ports, low battery warnings, all sorts of those wonderful things that you know that you are looking for when you go and buy a smart lock for your house. And all those things, those online reviewers, those first early adopters will comment about in those reviews that you will read when you go and decide which smart lock you're going to purchase. So hopefully that has given you guys some food for thought. And I'll see you next webinar, where I'm going to talk about something completely different, which is what the Weibull distribution is. But have a look at what that one's all about on Ascendo, and we'll go from there. Thank you very much for your feedback. And again, if you have any questions, feel free to reach out between webinars. You've got my contact details. But I think we're good, Fred.